In the next few videos, we're going to cover work and energy. This video is going to start by talking about conservation of energy, kinetic energy, and potential energy. Conservation of energy states that energy cannot be created or destroyed. We often express this with the following equation. The total initial energy is equal to the total final energy. This essentially just shows that whatever amount of energy you start with has to be the same as the amount of energy you end with. Again, energy can't be created or destroyed. Now, if you think about this, this seems maybe slightly different from what you might be thinking about, right? There are a lot of situations where we're talking about objects gaining energy or losing energy. And yes, that's true. In those situations, the object that we're focusing on is considered our system. And if you look at the change in energy of system, it can change, right? Our system can gain energy or it can lose energy. However, this conservation of energy isn't looking at just the system, it's looking at everything, the system and the surroundings. And when you look at the change in energy of the system plus the change in energy of the surroundings, you'll find that they always add up to equal 0. And that's essentially because if the system gains energy, then the surroundings lost energy. Essentially, the surroundings transferred energy to the system. Right? And same thing, if the change in energy of the system is negative, it lost energy, then that energy was released to the surroundings, which gained energy. So no matter what, the total energy does not change. Now, for physics, the energies that we're often looking at is kinetic energy as well as potential energy. So we can look at how these energies can be transferred, they can change in values, but the total energy cannot change. So kinetic energy is the energy due to the motion of an object. Now, there are many types of motion. There is translational motion, which we've been talking about for a while, where essentially the position of an object changes, right? The object is actually moving around. But there's also rotational motion where an object is just rotating or spinning. There's vibrational motion where an object is vibrating back and forth. And there's other types of motion as well. For the MCAT, we focus mostly on translational kinetic energy, which has the following equation. Kinetic energy is equal to 1/2 mv squared. 1/2 the mass times the speed squared of the object. Now, using this equation, we can figure out what are the units for kinetic energy. And 1/2, that's just a number, there's no units. M is mass, which has units of kilograms. Speed has units of meters per second, but since it's speed squared, we need to square the units as well. So that would be a meter squared over a second squared. These are the units for kinetic energy. Kilogram meter squared per second squared. And the unit that we usually use is the joule, which is a derived unit, right? Derived from the different basic SI units, and we usually denote this with a capital J. All right, so that's kinetic energy. Potential energy is the energy stored in an object. Similar to kinetic energy, there's several types of potential energy. There's gravitational potential energy, elastic potential energy, electric potential energy, and chemical potential energy, and many more. But for today, we're going to focus mostly on gravitational potential energy. In subsequent videos, we'll look at several of the other types of potential energy. Gravitational potential energy has this equation, mgh. You probably recall that gravitational potential energy is looking at how high your object is on the Earth. The greater the height of your object, the more gravitational potential energy it has. So similarly, looking at this equation, mass times gravity times height, we can figure out the units for gravitational potential energy. Mass is still kilograms, gravity is meter per second squared, height is in meters, so again, this is going to leave us with the same kilogram meter squared per second squared, so telling us that potential energy also has units of joules. And this should not be surprising because kinetic energy and potential energy are both energy. All right, so now that we've covered these topics, let's go ahead and look at a practice problem. So here we have a 5 kilogram projectile. It is fired with an initial velocity of 20 meters per second at an angle of 45 degrees off a 25-meter cliff. We want to know what is the speed of the projectile just before hitting the ground. All right, so as usual, it's always good with physics problems to draw out the situation so we can understand what's going on. So we know that there is a cliff, right? So this is a 25-meter cliff. And we know that we have a projectile that is fired with an initial velocity of 20 meters per second at an angle of 45 degrees. And as a projectile, we know it's going to follow a curved trajectory before hitting the ground. And we want to know when it hits the ground, what will its speed be? Now, if you think about this type of problem, it seems pretty similar to one that we've tackled before with kinematics, and that's absolutely correct. This is just a projectile. However, if you try to answer this question, solving for the speed just before impact, using the approach we went over before, the different kinematics equations, you'll find that it's very laborious. It will take many, many, many steps. And that's the case for many physics problems on the MCAT. There is often more than one way for you to get to the correct answer. And often it's helpful if you can figure out what is the fastest approach, the one that will take you the least amount of time, so that way you have more time to spend on other questions. For this problem, instead of kinematics, you should be using conservation of energy. So here, conservation of energy, we know that simply states that the total initial energy has to equal the total final energy. The energies we're considering are kinetic energy and potential energy. So we're going to be looking at the initial kinetic energy and potential energy, and that has to be equal to the final kinetic energy and the final potential energy. Now, in this situation, we know the equations for kinetic energy and potential energy, so we can expand this out into 1/2 mv initial squared plus mgh initial plus, this is equal to the final energy, so 1/2 mvf squared plus mghf. Now, in this case, one thing you should recognize is for potential energy, we're starting at a cliff and we're ending at the ground. At the ground, the height is 0, so there is no potential energy in our object in the end. So this whole term goes to 0. Another thing we can see from this equation is that every term in this equation has mass. If they all have the mass term, then we can go ahead and cross out that term. So that will leave us with 1/2 vi squared plus ghi is equal to 1/2 vf squared. We're trying to solve for the final speed, so let's multiply everything by 2. That will give us vi squared plus 2ghi equals vf squared. So finally, we can take the square root of both sides, and that will tell us that the final speed will be the square root of vi squared plus 2ghi. So the last thing we have to do now is just plug in the values for all of our variables. So the final speed will be equal to the square root of the initial speed, which was 20 squared, plus 2 times gravity. Gravity we know is 10 meters per second squared, times the initial height of 25 meters. And multiplying this out, we have the square root of 20 squared, which is 400, plus 2 times 10 times 25. 2 times 10 gives us 20. 20 times 25 gives us 500. So this gives us the square root of 900. The square root of 900 is 30. So that means our answer here is 30 meters per second. And again, using conservation of energy here is much faster than trying to do the calculation using kinematics.